fill in the dead air to just do an audio check. Check, check, 1, 2, 1, 2. Let's hop over here. Let's get the stragglers. Let me I'm gonna go ahead and get this to that. My attendance so I don't lose my work. Record this one. I'll be back to check attendance again as usual at around 10:15 to get the stragglers. Let me see. So I want to say the countdown has begun, quote unquote, right? So I think we only have 2 more lectures of new material. We have today, which is the last of the new material for exam 3. We take exam 3, it should become available next Wednesday at the start of class, and it'll be due the following Wednesday at the start of class. And then after next week is the last of the new material, which is going to be like a supplemental material. I'm going to pull it from another book, but basically it's already loaded into Pearson. Just keep kind of working like you've been doing. So yeah, we only have 2 more pieces of new material to cover. Then we'll start kind of reviewing for the final. Maybe we might work on a project or something, but so with that, you definitely want to take some time and go ahead and get Pearson in as much of order as you can as possible, right? And the order of priority, you definitely want to prioritize your exams first, right? So once you have, right now you still have access to all materials from Pearson. Again, exam 3 will become available next week. If you're going back over Pearson and trying to improve your score, you definitely want to get those exams in order first. The exams count for about 80% of your overall grade, right? So that's the least amount of work that you can do for the most amount of points. And then once you get your exams where you want them to be, and again, I mean, honestly, anybody can still get an A. Like even if you hadn't even started, you can get an A. Like you can get up to a 90%. I felt like a 10%, deduction was fair. That way, the chances of people getting a perfect score on the exam are like low, right? So that's why I don't mind, because if you get one question wrong, then the highest you can get is a B, which I think is more than generous for submitting something late, especially something like an exam, right? So again, the way I have everything set up, there's an automatic extension built in. I do want to remind everyone of the hard deadline. I think we're exactly like right at about 1 month out of May 1st, right? So as April wraps up, we move into May. That first week of May is the start of finals, right? So I think it's May 1st at 11:59 p.m. That's Sunday night going into Monday. Everything on Pearson is going to lock out, right? So you have right at 4 weeks. And then once we move into the week of finals, the only thing you're going to have access to is our final exam. And so the idea behind that is basically once you're done with our final, the idea is that once you're done with our final, that should be it. You should be done with the class. You shouldn't have anything lingering, trying to get old stuff, trying to submit documents and assignments past that point, right? So once you kind of finish our final, then you should be done with the class. Trying to think of anything else. I think those are the main points. And as always, if anything is not clear, if you have questions, comments, or concerns, feel free to unmute yourself just to get my attention, or type into the chat. I do check the chat periodically, but the faster response is basically unmute yourself during class. Also, you can email me and ask me questions. I just generally don't. I'll be too busy. I don't really check my emails, right? I don't feel like I'm Yeah, I just don't do it, right? So because I don't check my emails, that's why I try to go out of my way to be available during class time. And the intent is to use class time as like office hours or a study session. I just fill it with like the lecture and homework just to fill the day there. I feel like I feel like you all appreciate that kind of thing as far as like going through the lecture and working on the homework, because I could do this stuff in advance and just sit in silence during class time. I could do that, but I haven't. Okay. So with that, I can't think of anything else. So let's kind of go ahead and get the party started and finish out chapter 6. Okay. Yeah, a few additional further topics in algebra. And so today we're going to look at section 6.3, geometric sequences and series. So I think 6.1, let me see, do we have it? No, section 6.1, I think we just looked at sequences and series. And then 6.2 was arithmetic sequences and series. So arithmetic sequences and series were basically a sequence where you're given the initial term, and then basically you have this, what is it? Not common ratio. You're adding the same thing. Basically, you're adding the same thing each time, right? So given some first term, and then you're adding the same thing each time. So that was basically arithmetic is where you have a common difference, and we explore some of the concepts there and how to find the sum of the first n terms of arithmetic sequence. So then today we're going to look at what's called, again, geometric sequences in series. A few objectives here. We'd like to identify a geometric sequence and find its common ratio. We like to find the sum of a finite geometric sequence. We like to solve annuity problems and find the sum of an infinite geometric sequence. Okay. So we have the definition of a geometric sequence. The sequence that you see is a geometric sequence or a geometric progression if there's a number r such that each term except the first in the sequence is attained by multiplying the previous term by r. The number r is called the common ratio of the geometric sequence. So again, the common ratio is going to be your n plus first term divided by your n term, as long as n is greater than or equal to 1. So again, with this sequence or series, we're given some first term, and then all the subsequent terms are going to be the previous term times some common ratio, right? Times some common ratio. So in the previous section, we were adding the common difference. Now we're multiplying by some common ratio to generate these sequences. Okay, so let's look at it. Find the common ratio of each geometric sequence. Okay. Let's go here. So then, for instance, if we're working on part A, so we want to find that common ratio. So that's going to be the n plus first term over the nth term. So we can do things, it should be the same as 10 divided by 2, which should be the same as 50 divided by 10, so on and so on. And they should all be, what, 5, right? Forward. The common ratio we would do, it should be like negative 54 divided by negative 162, which should be the same as, you can do basically any term or divided by the previous, right? So I'm going to do negative 2 divided by negative 6. And you just want to confirm that these all work out. We get a positive 1/3. First term, multiply the first term by a third, we should get this. Multiply that by a third, we should get this, so on and so on. Okay. You see the 5 here, you see the 1/3 here. Recursive definition of a geometric sequence. A geometric sequence here can be defined recursively, right? So the recursive formula, so any term, the n plus first term is going to be the common ratio times the previous term, right? As long as n is greater than or equal to 1. This defines a geometric sequence with the first term a 1 and a common, wait a minute. Okay. Defines a geometric sequence with the first term A1 and common ratio R. To be augmented, but I'm going to let that be for now. So determine whether each sequence is geometric. If it is, find the first term and the common ratio. I feel like this is wrong. Let me look at this. I think I'm trying to, what it is that I'm trying to do is trying to generalize, and I think we haven't got to that part yet. So I'm just going to let this be for now. Determine whether each sequence is geometric. If it is, find the first term and the common ratio. Okay. So if we want to determine that these are geometric, let's list out like about 3 or 4 terms in the sequence, and then see can we find a common ratio, right? So then for part A, so for instance, when n is 1, we would get what, 4. When n is 2, we get 16. What is that? 40 plus 24 is 64. Let me see. 6 times 4, 240 plus 16, 256, so on and so on, right? So then are we multiplying what, 4 each time? I think we are multiplying 4 each time. So then we would say that this is geometric. So then the first term, so our A1 is 4 and the common ratio is 4. And let me shrink this down just a little bit. The first term, if n is 1, we get 3 halves. If n is 2, we get 3/4. If n is 3, 3/8. 3 what, 16ths? Half each time. So it looks like the first term is 3 halves, and the common ratio is 1/2. We're multiplying by a half each time. So I would say that this one is geometric. Down this a little bit as well. When n is 1, I feel like this one is not. 1 minus 5 is what, -4? When n is 2, 1 minus 25 is -24. When n is 3, it's 125, so -124. If we say -24, if this were geometric, right, the common ratio should be -24 divided by -4, which would give us what, 6. But then let's do 6 times 24. Let's see if that one works. Plus 24, 144, right? I don't think it works. So we're going to say it's not geometric. A is geometric and the common ratio is 4. Initial term is 4 and the common ratio is 4. Okay. Term is 3 halves and the common ratio is a half. Did we write that? Yeah. I think the last one we got no. It's not geometric. Not all pairs of consecutive terms have identical quotients, right? The quotient of the first 2 terms is 6, but the quotient of the third and second term is 31 by 6, right? So it's not geometric. to pause there. Let me go check Zoom really quickly. Just remind me towards the end of class, and then let me get these stragglers. So let's do like this. Back here. Start the broadcast. If you're just joining us, welcome. You know, the intro and the announcements are recorded. They should be on the YouTube channel. And so today we're working on section 6.3, which is the last of the new material for exam 3. And then after exam 3, we only have one more new section remaining. And so this section is on geometric sequences and series. The previous section, we kind of explored arithmetic sequences and series where we had a common difference and we were adding the same thing each time. So in this one, we have a common ratio where we're multiplying the same thing each time, right? That's the basis for these sequences and series. So then the general term of a geometric sequence. So when I paused earlier, this is where I wanted to kind of like do this, but I was like, well, maybe we're not there yet, right? So then every geometric sequence can be written in this form. You have the first term, then A2 is going to be A1 times the common ratio. But then if for A3, you're going to multiply that by the common ratio, you get this. The next one, multiply by R again. You keep multiplying by R, right? But R is the common ratio. Since A1 equals A1 times 1, which is basically A1 times R to the power of 0, the nth term of a geometric sequence is going to be A1 times R to the power of n minus 1, right? So, yeah, that's kind of how that goes for n greater than or equal to 1. So, sequence this, find each of the following. Okay. The first term, the common ratio, and the nth term. So then for part A, so the first term is blatant, right? A1 is going to be what? 1. And then for part B, the common ratio. So our R is going to be 3 over 1, which is basically 3, right? Because if you can verify it. Notice that 1 times 3 is 3, but that times 3 is 9, but that times 3 is 27, and so on, right? So we can be confident in this common ratio. The nth term is going to be the first term times R to the power of n minus 1. Right? 1, the common ratio is 3 to the power of n minus 1. So then the nth term is going to be 3, or we can probably just leave it as 3 to the power of n minus 1. If anything is not clear, if you have questions, comments, or concerns, feel free to unmute yourself and we can talk about it. We mentioned, let me see, I'm trying to think. I'm just trying to. So we mentioned on, I want to say there's like a blanket statement for anyone's grade, right? You just have to decide what you want to do. All assignments are still available with only a 10% late penalty. That means that includes old exams, old quizzes, and old homework, right? So you can go back to those old exams and you can get them all the way up to a 90%. To get a 90 at this stage, you would have to get a perfect score in the exam, but it's possible, right? Students do it, students don't. I leave it because everybody doesn't just take advantage of it, right? But really, at this stage, you just have to decide what you want to do and devise a plan and take action, right? It's okay to just sit down with your tutors and like link up. It's totally okay. Like just kind of get it done. Let's see. Yeah, you just have to decide. And then, but once you do decide to like see it through to the end and you want to improve your score, again, the order of priority, you want to prioritize your exams first because that's like 80% of your overall grade. So that's the most amount of points for the least amount of work. And then once you've kind of completed, once you've gotten your exams wherever it is that you want them to be with whatever you have access to, after that, I would work on the quizzes because the quizzes are only like 5 questions and that's like 10% of your grade. But then the homework, that's a lot of work for a little bit of points. I really don't want you guys to spend too much energy trying to get that homework in order. That's only 10% of your grade. The homework is really there to prepare you for the exams. All right, it's just practice and you get some credit. But I don't want you to stress out about not finishing that homework because that's a lot of wasted energy. And like, you got other things to do. My recommendation, again, just is get your exams in order because it's 80% of your grade. Once that's in order, then if you feel up to it, you can kind of work on those on old homework. But the bulk of the weight comes from your exams, right? So it's just a decision. You have to decide, make a plan to take action. That's all it is. And there are like extenuating circumstances where maybe every now and then like a student might need an extension or something like that or incomplete. But if you can avoid that and just get this done, ideally you want to get this stuff done and over. You don't want to have things lingering. Okay. Trying to think of what else. There are some other cases, but we'll kind of address those as they arise. Let's keep going. So we got 1, 3, and then 3 to the power n minus 1. So you can see 1 there for the first term. Common ratio was 3, and then 3 to the power n minus 1. Okay. Nice. Okay, let me there, but we're going to try to work with as if we didn't see it. Find the 23rd term of a geometric sequence whose first term is 10 and whose common ratio is 1.2, right? Okay. Said, let's do this in green. The nth term in the geometric sequence is going to be what? A1 times r to the power of n minus 1. That. Find the 23rd term. It's 10. Common ratio is 1.2 to the power of 23 minus 1, right? And I think you would just use a calculator at this point. All right, let's use the calculator. 10 times 1.2 to the power of 22.
2 to the power of 22 is approximately 552.06.
So that's all. I think it's just the same thing. Of the terms of a finite geometric sequence. Let this sequence be the first n terms of a geometric sequence with the first term A1 and a common ratio R. Then the sum Sn of these terms is given by this. Let me think about this for a moment. With the previous, I want to derive this. I want to see, generate this result, right? Where does this come from? Let's just have some little bit of fun. You don't really need to know this or do this. I'm just doing this just for the sake of doing it, right? So we want to consider a geometric sequence. And we want consider the sum of the first n terms of the geometric sequence, right? So that's, if the sequence is geometric, that means it's gonna be what? The first term plus, the second term is gonna be what? A1 times R, A1 times R squared, and then the nth term is gonna be A1 times R to the power of n minus one, right? So that's gonna be the sum of the first n terms sequence. Now, let's take this and multiply both sides by R. So if we multiply R on the left, we get R times the sum. And on the right, we're going to get R A1 plus R here. Let's write it. Let's be consistent. Times R plus A1 R squared. It's going to be what? Minus 2. A1 times R to the power of n, right? Because we're basically adding 1 to each exponent. So then now let's say the first sum, let's subtract these two. If we say the line 1 minus line 2, if we subtract them, we're going to have Sn minus Rsn, right? Now, if you subtract these two, you should notice something should happen, right? What do you notice? If you subtract, and you basically through what, you can rearrange them, you can look at it kind of like the following, all right? You can consider like there's a 0, and you can just shift it. So you can line up the like terms. If you line up the like terms and subtract line 1 from line 2, if you say this and distribute the negative and add all these together, right? Cancels this one. This one cancels this one. There's going to be a term there that's going to cancel this one. I think this one's going to be canceled, and you're just going to be left with that guy there. So then when you subtract these two, A1 minus A1 R to the power of n. On the left, we can factor out the Sn. We're left with 1 minus R. On the right, we can factor out the A1. We're left with 1 minus R to the power of n. And then through algebra, you divide, then the sum of the first n terms of the geometric sequence is going to be A1 times 1 minus R to the n over 1 minus R, right? Right. Okay. So now we see where the sum of the first n terms of a geometric sequence comes from. And I feel like when you're able to derive these formulas, that gives you a better appreciation for them, knowing how to use them. And some of these techniques come out in like advanced mathematics techniques, like for solving just some advanced mathematics concepts and things. So you guys actually are doing advanced mathematics, because you can't do advanced mathematics without this stuff, right? Okay. So you're geniuses is what I'm getting at. You just don't know it. And I'm here to wake you up. Like that's the role I've given myself. So anyway, and it doesn't have to be in math, right? You can take these concepts and apply it to whatever you love. That's the power of the genius. That's the beauty and the creativity and the genius of the genius, right? Is that, yeah, you might not be good at math, but you can like take this and apply something that you experienced here, apply to something that you do love, something that comes natural for you, right? Whether it's music or communication or writing or creative writing or politics or business or whatever it is, you can take something here and apply it to something that you love, right? This is just one of my loves, right? And this is how I express myself. Okay, so finding the sum of terms of terms of a finite geometric sequence. Find each sum. Okay, let me see. So now we just said, let's kind of recall what the conclusion we just arose to. Let's put this in green to be consistent. So we said the sum of the first n terms of a geometric sequence minus R to the power of n times A1 over 1 minus R. I think that was it. then if we work on part A, so the sum, first 15 terms would be the first term. So when I is 1, if I is 1, I think we get 5 because this term is going to be 0.7 to the power of 0, which is going to be 1. So then that's 5 times 1, which is 5, right? So the first term is 5. 1 minus the common ratio. I think the common ratio is 0.7. Let me write out the first few terms just to confirm that the R is 0.7. So when I is 1, the first term is 5. Then when I is 2, 5 times 0.7, so 3.5. When I is 3, 0.7 squared, 0.49. Hey Google, what's 5 times 0.49? Should be just below 2.
5 times 49 is 245.
45. Right? Hey Google, what's 5 times 0.49?
5 is 245.
She can't hear the decimal. Okay. We'll try one more time. Well, that's fine. I know this. Okay. I think let's do one more. 1, 2, 3, 4. So when I is 4, 0.7. Hey Google, what's 0.7 to the power of 3 times 5?
That's 5 is 1.715.
1.715, right? Okay, so let's confirm that we're multiplying by 0.7 each time. Hey Siri, what's 5 times 0.7?
0.7 is 3.5.
Hey Siri, what's 3.5 times 0.7?
0.7 is 2.45.
Hey Siri, what's that answer times 0.7?
Times 0.7 is 1.715.
Okay, so we confirmed that the common ratio was 0.7. So let me just kind of move things around a little bit. The common ratio was 0.7 to the power of n. N is what, 15 in this case? Need to use a calculator. Let's do parentheses, 1 minus 0.7 to the power of 15. Let's do 1 minus 0.7. You get approximately 16.59. Let's see. Now we have the same thing, but now instead of saying I to the power of, instead of 0.7 to the power of I minus 1, now it's 0.7 to the power of I. So let's list out the first few terms to confirm that this is geometric as well, right? So for instance, 1, so I think it's just shifted, right? It's just shifted by 1. So then instead of starting at 5, it should go 3.5, 2.45, so on and so on, right? But it still looks like we're multiplying by 0.7 each time. So then for B, the sum of the first 15 of this geometric sequence is going to be A1. The first term is now 3.5. 1 minus 0.7 to the power of 15. The same. Recall this and change that first term. So I'm going to insert 3.5. Okay, so these are the results that we got. 11.61 and 11.61. So the value of an annuity. So I don't want to keep, let's kind of hang out for like a little bit, about right at 7 minutes. If we don't finish, I'll let you go, but I'm going to finish this stream. So let P represent the payment in dollars made at the end of each month of n compounding periods per year, and let I be the annual interest rate. Then the value A of the annuity after T years is given by this, right? So 1 plus I over n to the power of nt minus 1 over I over n. So this looks like the compound interest formula. Let P represent the payment in dollars made at the end of n compounding periods per year, and let I be the annual interest rate. Annuity after 2 years is given by this. So I think this is factoring in like how often the annuity is being applied. It's similar to compound interest formula, just with like this adjustment, right? Individual retirement account, IRA, is a common way to save money to provide funds after retirement. Suppose you make payments of $1,200 into an IRA at the end of each year at an annual interest rate of 4.5% per year, compounded annually. What is the value of this annuity after 35 years? All right, so let me see. I think I might remember that formula. BP times 1 plus, it's usually I over n to the power of nt, then there was a minus 1 over I over n. N to the power of nt. You don't need to memorize this, you just need to know how to use it, all right? Let's identify the different components. Individual retirement IRA is a common way, blah, 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 blah. Suppose you make payments of $1,200, let me see, into an IRA at the end of each year at an annual interest rate of 4.5% per year. Okay, so for instance, because it says compounded annually, that means our n is 1, right? So that's how many times the interest is applied in a year, right? So it's only applied once per year for this one. The interest rate is 4.5% per year. Usually that's as a decimal. So I'm going to write, so that's going to be our I, but I'm going to write it as a decimal. So 4.5, you divide by 100, 0.045. We got I and the principal, and I think this is an I right here. Because usually that principal is a one-time deposit, but this one seems like it has deposits each year, right? Let me see. We let P represent the payment in dollars made at the end of each of n compounding periods per year, right? So the P is the amount deposited each year. So I think we're okay. We can just go with the formula. So then we can plug in the different components. Let's write it out. It should be 1200 times, we got this one plus our I, 0.045 over 1, so we don't need that part. And 1 and T, 35 years. This is right. We just plugged in the different parts into the formula. We're going to use our calculator. So let's do 1200 parentheses 1 plus 0.045, and that part to the power of 35, right? We're going to say minus 1. Then close off the numerator. Let me insert one more set of parentheses. 0.045. Let me see. Close, close. I think we're good. So please, this makes sense. If this is retirement, you're adding $1,200 for $1,200 a year for 35 years, 100,000. Okay, we're talking about a retirement account. I think that's the reason that can happen, right? So then we get approximately. See the time. We're almost there. We got 7,000. I need to get started, and this is doable. I can be more aggressive. I need to. I'm going to go look and see what kind of IRAs I can find, because I could be more aggressive than that. I can be way more aggressive. But anyway, I'm sorry. And if you guys start, like, the sooner you start this stuff, the better off you are. But anyway, the thing I struggle with is, like, because we don't know when we're going to check out of here. It was weird because, like, my dad was like, when he was planning for his retirement, he was like, you got to ask yourself, how long do you expect to live, right? And you want to try to build around that. And like, when he said that, it just sent a chill through my body, because but he's not here anymore. I mean, that's how these things go. Thank you. I know. Thank you. Okay. So we get this, all right? Almost 100,000. Let's see, how do we do? Okay, this looks good. I think we got the same thing, right? All right. The value of the R 35 is this. Okay, that's fine. Let me pause right here. I know there was a student that requested to speak. I tried to answer what I thought your question might be. I'm almost done, right? I got like a few more slides. I do want to get through these, but that is the official time for class, so I don't want to hold the general population. So if you don't have any questions, and if you need to go, you're free to go. I'm going to go ahead and finish these last few slides, and then when I'm done, hopefully the student is still available, and we can kind of chat about whatever you need to chat about. Okay, but we're almost done. That's the only reason I'm keep going. Okay, so then this last concept, it says the sum of the terms of an infinite geometric sequence. So previously we added up the first n terms, right, where it cut off somewhere. So now, what if the sequence went on forever and we wanted to add them up, right? So then it almost seems like, well, if you added up something that's infinite, how can it add up to a number, right? Well, these things converge, right? So if the common ratio, if the absolute value of the common ratio is less than 1, then the infinite sum is given by this guy here, right? When the absolute value of the absolute value of the common ratio is less than 1, it converges. It'll shrink down to practically 0, and it converges to this. Okay, I think it's that value of R, I want to say is greater than 1, it doesn't converge and there is no sum. Like if this symbol is flipped, it doesn't work. Right. And then for this derivation, I just want you to see this real quick as well. So when we had the sum of the first n terms, right? So the sum of the first n terms, I think we said it was A1 times 1 n over 1 minus r, right? That's the sum of the first n terms. So then if you let the ratio be, the absolute value of r be a number smaller than 1, so it's between 0 and 1, when you let this n run to infinity, when you have a fraction that's between 0 and 1 and you keep multiplying, like you raise it to a very, very large power, that fraction gets really, really small, right? So this only works because the absolute value of the common ratio is less than 1, right? So again, when you let this n run to infinity, this term essentially goes to 0. So if that goes to 0, on top we just have A1, and on bottom we have 1 minus r, and that's where this comes from. Hopefully that makes sense. Okay. So I just wanted you to kind of make that connection. Again, it's only work because the absolute value of r is less than 1. Absolute value of the common ratio is less than 1. So we're asked to find the sum, right? So we have the first term. Let's find the common ratio. So then r should be 3/2 divided by 2. If you flip and multiply, it looks like 3/4, right? So let's confirm that we're multiplying 3/4 each time. So 2 times 3/4, 3 becomes 3/2, right? This times 3/4 is 9/8, then 27/32, right? So the common ratio is 3/4. So notice that the absolute value of r, which is going to be the absolute value of 3/4, is less than 1. So we're in the green to find the infinite sum. All right, that means the sequence is going to converge. Okay, so then we said is going to be A1 over 1 minus r, because the absolute value of r is less than 1, right? So the infinite sum is going to be 1 minus 3/4 under 2. What, 1/4, you flip and multiply, looks like it adds up to 8. If r is less than 1, then we can use this and we get this result. That was fun. I told you we didn't have that much more. It took like 5 more minutes. All right, okay. So I know that there was a student that had a question. Are you still on the line? Are you still there?
Yeah, I'm still here.
Other than the student, have any questions before we kind of end the stream? If you didn't mind going on YouTube, okay. Aside from the student, if there aren't any burning questions, we're going to end the session here. Let's see. And then so for Friday, we're just going to work through the homework associated with this topic, right? And so from one beautiful mind to another, enjoy the rest of your day. Let me end the stream and hop into this private session.